This will be an example on how to find electric displacement D. I have written some theory that I will need. I have Gauss's law. The closed surface integral of E dot dA is equal to the total charge enclosed over epsilon naught. And I want to remind you, this charge enclosed, the total charge enclosed, includes both the bound charges and the free charges. Everything. What you place there and what you get due to polarization of any insulating material around it. Now, on the other hand, equation 2, this is the closed surface integral of d dot dA, the electric displacement dot dA, and this is equal to the free charge enclosed, and the free charge is what you place there. This does not include any charges from polarization. Now I have also written the definition of electric displacement, and I will also need the infinitely small dl vector written in cylindrical coordinates. And the reason why I'm gonna go with cylindrical here is because I have a line charge density. It's a straight line. The charge density, the linear charge density is lambda. This is surrounded by insulation that has a radius a. And what the goal is from this problem is to find the electric displacement D. Now, the way that I will do that, I will apply equation 2. Now, for this, I need to choose a Gaussian surface. And my Gaussian surface will be a cylinder. So, this is the side view, by the way. It is difficult for me to draw a cylinder on the 2D screen. So this blue thing is gonna be my Gaussian surface, and this is a cylinder, as well as the insulation. Both of them are cylinders. I just have the side view here, so let's make a note. This is the side view. Gaussian, right, I got a typo. This is my Gaussian surface. So I'm gonna start with equation 2, and I'm gonna start with the right side. So I need to find the free charge that is enclosed by my Gaussian surface. Now let's do the following. Let's say that this radius is s, and let's say that from here to here this is length L. Alright, let's write it here. So this is L. Now since it is a linear charge density, to find the charge enclosed, I will need to do from 0 to L my charge density times dx. And one thing that I can do is I can choose my coordinate system. Say, since I'm going from 0 to L, let's place the 0 of my coordinate system here. This is the x direction. Now, since I'm gonna use notation consistent with my cylindrical coordinate system, so I'm gonna set the z to be here. This is my z-axis, and then from here to here, this will be my s. I cannot show phi hat, the phi hat unit vector here. Alright, so I'm integrating. I'm gonna go back and change this. I'm not integrating over x, I'm integrating over z. Oops. So this is gonna be lambda dz, and because I'm told from the problem that the charge density is uniform, I can take it out of the integral, and I will have from 0 to L dz. This will give me time the charge density times L, which, if you think about it, you got a constant. The linear charge density is coulombs over meters times the length in meters. You should get, by multiplying these two, you will get the total charge enclosed. Now keep in mind, this is only true because the charge density was uniform. If your charge density has any dependence on z, then you do have to do the calculation of the integral. And of course the result will not be just the charge density times the length. Alright, so this takes care of the right side of equation 2. Now I do want to point out, okay, physically what happens. When I place a linear charge density, and I surround it with insulating material, my insulator, I know that my insulator will be polarized because the charges of the linear charge density will create an electric field around them. And that electric field will polarize the atoms and the molecules of the insulator. So, what do I have? Okay, you have to keep this in mind. You do have those free charges that you placed there with the linear charge density lambda, but as a result of the electric field created from those charges, you will also get dipoles, induced dipoles, inside the insulator. And that's what we call the bound charges. Alright, now on the right side, working with equation 2, the right side is just the enclosed free charges. I did not have to worry about my dipoles, the induced dipoles. If you see, my Gaussian surface does include part of the insulator. The thing is, I don't have to worry about those dipoles because equation 2 is only talking about the free charges. Now, alright, so now I'm gonna move on with the left side of equation 2. As usual, I will need to write the electric displacement vector as a vector in the cylindrical coordinate system, and I will also need to write dA in the cylindrical coordinate system so that I can find the dot product. Now, I know when you have a linear charge density, you do anticipate, you can predict that the electric field will go, okay, assuming it's an infinite, the electric field will go in the radially outward or inward direction depending on the sign of the charges. Now, I will make the assumption that the polarization, that depends of course on the induced dipoles, is also pointing along the same direction, either inward or outward. Now, that will be the S hat direction. According to my cylindrical coordinate system, this is the S hat direction. So what I would do here, I would say the vector D, this one, the vector D, I can write it as ds times S hat. Now for dA, this is a little bit more difficult to show you on the 2D surface. I will show you the process. I have written my infinitely small displacement vector dl in the cylindrical coordinate system, and I can make a note. Throughout this problem, I will be using here I am using the cylindrical coordinate system. Now, the infinitely small area vector that I want to find is created by taking a small piece. This is my dA, my small area. Okay, this is my small area. Now, of course, the dA vector will point towards you out of the screen, because by definition the area vector is perpendicular to the actual area, and also it points away from the closed surface. So the dA vector is pointing towards u. Now, for the cylindrical coordinate system, okay, this side of my small area will be a dz, and this side will be s times d phi. This means, in order for me to find the infinitely small area vector, first of all, I know that it's pointing in the s hat direction, and I also know that the size of the area is s d phi times dz. I'm just multiplying the two sides of that small area vector. So now what I'm going to do with these two, since I need to find the dot product between d and dA, I will have ds s hat dot product with s d phi dz s hat, and I can take everything else out, so I will have ds s d phi dz, and I have at the end the dot product between s hat and s hat, but I do know when you find the dot product between those two vectors, you get 1. Both of them have a magnitude of 1 and they point in the same direction, so the dot product will be 1. Alright, now now that I found the dot product, now I need to use this on the left side of equation 2. So I'm starting, it's the closed surface integral of d dot dA, and because I'm integrating over phi and z, phi will go from 0 to 2 pi, it is a cylinder, and z will go from 0 to L, and then I have ds s d phi dz. Now I can take, there is no, in this integral, d and s, they don't depend on z and phi, so I will have ds s. From the integration over phi, I will get the 2 pi, and then from integration over z, I will get the L. And now I will need, now that I have this result, I need to combine the result from the right side of equation 2 and the left side. So let's call this will be equation 5, and this will be equation 6. And using 6 with 5, actually, and equation 2, solving for ds, I have a cancellation of L, and it will be lambda over 2 pi s. And if I want to use this this is just the component, okay? Keep in mind, this doesn't give me the vector. This gives me the s component of the electric displacement. If I want to write the vector d, then d will be the component ds times s hat, and using what I found, the vector d will be written as lambda over 2 pi s hat, and let's call this equation 7. And now I have found the electric displacement, which was what the problem was asking me to find. Now, one thing that I want to mention, inside the insulation, of course, there will be polarization. Okay, so this vector P will not be 0 inside the insulation. However, outside, so here, because there will be induced dipoles, this P will not be the zero vector. But outside the insulation, where there is air or just vacuum, of course, there are no induced dipoles. So the vector P for polarization is exactly zero. Now, if I use equation 3 and my result from 7, so I can say now, okay, I'm done with this part. I can say outside the insulation, meaning when S is greater than A, I know that P is 0, so using equation 3 and a P equals 0 will give me epsilon naught times the electric field, and this means I can find the electric field outside the insulation as lambda over 2 pi S times epsilon naught, and that will be in the S hat direction. Okay, this is epsilon naught, and this, let's call this equation 8. Now, if you're interested to see what happens inside, where S is less than A, then what I have from equation 3 is that D is equal to epsilon naught times E plus the polarization. So if I want to find the electric field E, which, by the way, that's the total electric field, this is what you actually have inside. If you measure the electric field inside the insulation, you're measuring E. If you want to find E, given that we have the electric displacement from equation 7, then somehow we need to know the polarization P. And unless somebody tells you, unless you have a way of finding out what is the polarization vector, there is nothing else you can do at this point. You found the electric displacement, and if you don't have any more information about polarization, you're done. You stop here. But outside the insulation, you have the ability of finding E.